Hello, my name is Joel Fischer. I'm the lab manager here at AMETEK MOCON. I oversee our permeation laboratory that has nearly 100 instruments that measures oxygen, water vapor, and CO2 through various materials and packages. What I'd like to do today is give you an overview of what is permeation, how it's tested, some things that factor into those types of results, and the different types of materials or packages that can be analyzed. So for this study or this presentation, I'm going to start with what we call the poster. This is actually something that's outside our laboratory. We used to explain what permeation is, why permeation matters, different test methods, also some things like what does permeation look like, how long does it take, and also kind of finish off with applications. What are the things that we analyze? So to start off, we're going to focus on what is permeation. So what is permeation is a question that we get. We're measuring transmission rates all the time. It's what our core instrument does. And kind of simply stated, I think the schematic does a nice job, it's a three-step process. We'll have a gas. It's usually a test gas. It could be oxygen, water vapor, CO2. We've got a barrier material. It could be a bottle wall. It could be a film structure for a pouch. It could be lidding on a tray or the tray itself. And then we've got the other side of that. So what permeation really is these molecules, we call it the test gas side, they'll have a high concentration and they'll absorb into the surface of that material. They'll diffuse through and they'll come out on the other side. What drives permeation is really a concentration gradient. Molecules don't like to be contained, so if you've got a high concentration on one side, a low concentration on the other, it's going to permeate through, or it's going to move through the material. How it moves through, we're going to talk about a little bit, but that's kind of what it is, this three-step process. One thing I like to talk about is an example of that, kind of envisioning, is a carbonated soft drink. You've got your bottle, your PET bottle. It's nice and taut. A lot of CO2 inside the bottle, whereas in atmosphere, there's not as much. So what happens over time is the CO2 will diffuse through the bottle wall, and over time, you'll lose fizziness in your soda. And a lot of people think that it's leaking out the closure, which really isn't the case. So when you look at the polymers used for bottles, you might see them lightweight the polymers, make them thinner for things like water. However, if you have a really thin bottle for a carbonated soft drink, it's not good enough. You lose the carbonation just so quick through that thin structure. So the bottle wall and the thickness of the material does impact the net transport and net transmission rate of CO2 through that bottle. There's physics behind it. It's not just a made-up fact. Fick's law is known to really kind of control or define what's going on with things. Again, we could have like a pouch structure here. Maybe that's a liquid in there. Could be a serum, could be a drink pouch and the like. You may have water vapor on the inside because you've got, it's a wet product, high concentration, and ambient humidity is usually much lower. And then what's going to happen is the water vapor is going to want to permeate out of the pouch into the atmosphere from a high concentration to a low concentration. The amount that permeates out is the flux, and it's a relationship between what we call a diffusion coefficient, which is how these molecules wiggle through the polymer, and then also that concentration ratio and the thickness of the sample can factor in there. For an example, if I use a higher concentration, maybe I'm doing an oxygen test. If I use 100% oxygen on one side of the structure versus room air on that same side of the structure, the 100% OTR is going to be 4.78 times higher. So concentration does impact the net transmission rate. It kind of makes sense. If you're talking about water vapor, if you've got a moderate humidity that's challenging the material, like 50% RH versus 100% RH, the 100% RH is going to let more water vapor permeate through the sample. When we look at the units of measurement for gas transmission rate, typically what you see in oxygen and also CO2 is a volume of gas normalized to an area per time. For water vapor, because historically things were done gravimetrically, and when they measure weight loss or weight gain of a cup test, they used to call it, they measure it in terms of grams per meter squared day. So a little difference here. When we look at oxygen, CO2, we're focusing on volume of gas in the material. Here we've normalized it to the weight of the water over time. The next slide we're going to focus on too is really like, why does it matter? It matters for a big reason. It's for performance of products. And permeation behaves in all these different levels. What I mean by that, you have some things like here, and this is a log scale of oxygen on the y-axis and water vapor on the x-axis. We've got some very breathable components here up high. Breathable might be like a building wrap, where water vapor needs to breathe so you don't get excessive condensation and moisture and mold buildup, but you don't want liquid water to go through. For things like produce packaging, things that need to be breathable because there's respiration going on with the produce. If the packaging was too tight, you might one of the byproducts would be like an ethylene gas, that then causes it to ripen faster. So having breathability, it kind of decreases that ripening rate. So you've got good fresh products in the grocery store. If we look at consumer goods or things like potato chips, potato chips are put into a pouch. If you look at the pouch, you open it up, and it's metallized. What's kind of neat about that is that it's not there to look pretty. That metallization is there to put better barrier in, because when that potato chip is sealed within the pouch, they actually flush it with a dry nitrogen gas and then they seal it. The dry nitrogen gas does two things. One is it pushes out oxygen. So there's a low oxygen level in there to help with reduce any rancidity of the oils on the chip and extend the shelf life. Also, the dry aspect of it also keeps the chips nice and crispy. You wouldn't want to bite into a chip that isn't soggy. So for material or for a product like potato chips, you need good barrier for both water vapor and for oxygen. You kind of go down this chain, you look at pharmaceutical serums and drugs and things like that. They have to maintain their efficacy, that they have to be good, at the time of use. So the shelf life of the product is very important. Electronics as well. We want our solar panels to work really well over long times. And OLED screens down at the very lower left corner, very high barrier materials. The screen that you see on these television sets, they have a coated structure that you're looking through. They have to be nice and clear, but they also have to be a very high barrier because the electronics behind them can degrade with moisture and humidity. So that you need these really great barriers for us to have these really nice TV sets. So the takeaway is that when we look at permeation, we're going to be looking at them over quite a range. Things that could be very breathable or things that are really high barrier. One point I'll just put out there is like not one instrument can measure all of these. Instruments are kind of like for oxygen, they'll have some that are really good at high transmitters and some that are very good at low transmitters. Same thing for water vapor as well. You can kind of get that. If you're going to measure distance, you wouldn't use the same tool to measure miles between two houses that you would use to measure your height or the details on an electron microscope. You need the right tool for the right measurement. The next thing I want to talk about is factors that influence permeation. The first one I want to talk about is temperature. That's a biggie. That's really important. We talked about the 3 steps of molecules moving through a sample. They absorb, they diffuse through, and they come out the other side. That diffusion coefficient, as we talk about, is kind of like how fast they wiggle through the matrix of the material that they're permeating. And when you add temperature, you're adding energy, and those molecules move faster. So what happens is, here's a just example of a material that if it's analyzed at different temperatures, you can see a higher, in this case, it's a permeation rate going on with that. More flux goes through, more water goes through, more oxygen goes through. So it's kind of important what temperature are we analyzing at. The examples, typically water vapor has been standardized around 37.8 C, which is 100 F. So you'll find a lot of spec sheets around that, which is near like a human body temperature. Oxygen is more commonly done at ambient temperature, around 23 C. So temperature is important. So if you're thinking about, hey, I need to test my sample and I want to know, what the transmission rate is through it, you kind of have to be thinking about, am I trying to get numbers that can compare to other other values, other literature values, then you should use that same temperature. Or are you concerned about how does my cheese behave, or my milk behave, or my refrigerated product behave, with the barriers around it, with the packaging around it? And if that's the case, then you look at testing at that temperature where it's really going to be stored in. So that's always a debate. What temperature should I test this property of permeation? And it's an important choice here. Humidity level is also important. It directly relates to a water vapor test. If I use a high humidity exposure, such as 100% RH, I'm going to get more water vapor transmitting through it. If I use a lower humidity, such as 50% RH, then I'm going to get less water vapor permeating through it. So that's important. You can stimulate maybe real life conditions to understand what's going on with your packaging in your product inside and the protection, like that. Time. What's interesting about time is that samples don't come to equilibrium like immediately. Unless there's like super high transmitters, like a silicone or a Teflon or things that are super high like that. So it can take some time to actually run a test. And if you don't run long enough, you may not get like the equilibrated or final value. So that's important. You kind of look at criteria of how long you're running a test or how long this is going to happen. Material type is important. There's definitely different barrier levels. This graph below, let's see if I can get this on here as well, kind of shows low density polyethylene, much higher transmission rate than biaxially oriented polypropylene. So some materials are innately higher transmitters, others are innately lower transmitters. Some have multiple layers to get the barrier properties that you need out of the structures. Thickness is important. When you have a sample that's thicker, let's say if you double the thickness, then that flux, that gas moving through it is going to cut in half because you've got all this extra barrier. So the outcome is normalizing the thickness can be key, but many times people want to know what's going through my tray, what's going through my pouch. So what is going through this tray of this thickness for OTR? It's something to consider. And so if you need more barrier, you can make a sample thicker. That's a common thing to be done. If you think of the bottle I talked about with the carbonated beverage, with a soda pop bottle, it has a nominal thickness. These water bottles, some could be very, very thin. But if you look at a vitamin water, where they've got vitamin C in there and they're worried, you don't want oxygen to permeate in and degrade the chemistry of the vitamins, they actually have thicker bottles for those. So a lot of the vitamin waters or the energy drinks have an even thicker bottle for the shelf life of now the vitamins and stuff inside. Barometric pressure can also play a factor in it. It's more for gases like oxygen, CO2, where if someone is testing in a different location, just because there's different atmospheric pressures around us, if I was in Denver, there's less gas around me, so it ends up being that when I run an oxygen test, I'll get a lower transmission rate, unless I have something like built within the equipment that measures my pressure and then normalizes it out. Our equipment, our MOCON equipment, does that. So whether you are testing in Denver or here in Minneapolis, where our facility is, you're going to get a good and repeatable transmission rate. The next thing I want to talk about is humidity and the role that humidity can play. There are some materials where humidity can permeate in and then cause it to swell. I think if I take things to an extreme, you can think of like a coated paper. The coating helps, protect it, doing some good things, but once water vapor permeates into the paper itself, it can swell, it can cause some cracking, some stress to strain in the coating, and it can change kind of the overall properties of that structure. There's some polymers that kind of do that as well. This is a nice graph, and it's on a log scale looking at OTR with different polymer types and different humidities. And what you'll see is there's some polymers, basic polymers you see a lot, like polyethylene and polypropylene, that are fairly, I'll say, insensitive to moisture and humidity. They don't really change much, whether I have a high humidity around them or low humidity around it. The OTR or the CO2TR would remain constant. There are other materials, though, like classically an EVOH is one, nylon is another one, where if I test at a low humidity, I'll get a lower transmission rate than if I go up to a high humidity. It doesn't look as extreme here because this is a log scale, but in real life, it's a big deal. So when people incorporate things like EVOH or nylon into structures, into a nice pouch structure, or to like a coffee cup or capsule, that they put those in there to keep let's say the coffee nice and fresh, good oxygen barrier. But they may then protect it by putting these other layers around it to protect that layer from moisture around there and changing that OTR. So there's a lot of good thought into materials and the structures when they're assembled and they're put together based on what are the barrier properties that you need. So if you can think of a multi-layered structure as an EVOH, which here is a relatively good barrier, embedded within polyethylene, you'll see, boy, it'll do a great job of bringing that polyethylene down quite a bit when you put a multi-layered structure together and kind of stack them together. So that's good. This next piece I wanted to talk about is the method itself. How do we test for this thing called permeation? The way we do it is like the original schematic I showed you, where we had a barrier film, we had a film, and we had a test gas challenging on one side, and we had a carrier gas or a different gas on the other. We actually use the same configuration, but we mount the sample in something called a diffusion cell. So the diffusion cell is this round cell. This is a cross section. You can see the film sample here is mounted in place. For a water vapor test, what we have is we're going to put a controlled humidity here. We can have a precise humidity at 35% RH, 50%, 90% RH if you want a very high humidity. We could actually turn off the flow and put a wet sponge underneath here and have 100% RH underneath the film. On the other side of the structure, we could have in our dry nitrogen carrier gas sweeping over here. And really what's going on is with this constant sweeping of gas across this face of the film, any water vapor that permeates across the film gets swept by this gas to a detector. In this case, it's a pressure modulated infrared detector tuned specifically for water vapor, where it's quantified. And that's really the gist of the test, is we need to set it up, the film up in a way that we can provide a known and constant humidity. We can provide a known and constant dry gas on the other side. And we've got an instrument that can measure it, which is really nice. There are a lot of caveats around this that, you really need great temperature control. Our system's controlled to 0.2 degrees C. Very, very, very good control, very good humidity control, which is good for consistent, good, nice results. Typical test conditions, maybe for water vapor, you'll see like an ambient temp with an ambient humidity. Things that are really common though in industry for spec sheets would be like 38C and 90% RH or 38C and 100% RH. What's nice about 100% RH is it's kind of a worst case. And it's also very easier to set up and control because it's a controlled system here with just a sponge underneath the film and no flow. Helps be good repeatability. This methodology is classically known as ASTM F1249, but internationally there's other standards too. There's ISO 17106. There's Japanese, Chinese standards as well around this test for water vapor transmission rate. For oxygen, it's really very similar. It's identical almost. You've got a diffusion cell. We'll have oxygen that's going to flow on one side. We'll have our nitrogen plus hydrogen carrier gas flowing on the other side. Any oxygen that permeates through gets swept by this carrier gas to a detector and it's quantified. Again, there's ASTMs and there's also other international standards around here. And by far, if you're going to look up any kind of literature or values on OTR, you're going to find them most often done at 23C with dry gases. So really, that's the standard kind of around it. And that's the way that test runs. Now, here in our laboratory here at MOCON, we get asked a lot like, hey, I'm setting my film in. I'm going to run a test. How long is it going to take? So we get asked that, how long will the test take? And the answer is we don't know. We could set up the test and run oxygen on one side and then run this nitrogen on the other and start taking data. But how long does it take for the sample to get done and come to equilibrium? And that's a great question. And the answer is we don't know until we run the test. Now, we may have a good idea if we know what the material is and how thick it is, but it can really vary quite a bit. This graph here kind of shows like for like a low barrier sample, maybe a polyethylene, a thin polyethylene used for a wrap or a tray or something like that. It might come up very quickly in a matter of hours and reach equilibrium. Or it could be something where that OLED or electronics, super high barriers, or barriers used in medical and pharmaceutical with their foil packaging or their high barrier trays and lidding and the like. That we may actually see things come out of it. It just come down to a very, 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 very low level. You may wonder, why is it coming out? I think that's a good question. So you may be wondering, like, why would I see this outgassing from the sample and things come out or come down to a low level that graph was showing? If I kind of go back to this initial schematic or initial photo of the diagram of permeation, where we've got a test gas here, we've got a barrier film, and we've got our other structure here. And this is where our nitrogen carrier gas would sweep. Think of a structure that might be like a foil pouch. You may have a great foil layer here, and then you'll have like a polyethylene layer that helps you heat seal and bond the pouch together. Maybe it'd be another layer outside the foil. So this would be a high barrier material. If we're going to run the sample, people think, oh, you're just going to see nothing coming out of this. But the reality is that this material is out in ambient air. And the polymer and our film materials and things that we're looking at absorb oxygen, water vapor, these gases just from ambient. They're kind of like the sponge. So when we first mount this and put this on the instrument, it's very common to actually see, let's say if there's a foil here, but a polyethylene layer here, or some sealant layers here, that what's absorbed within this layer that's going to be facing my product when I make the pouch or make my package, we're going to actually see it come out, diffuse out of it. It'd be just like a sponge kind of drying out. We're going to see that level. So that's what gives us that curve of when we see an outgassing curve, things coming very, very low, and then going down almost near zero. Is that our equipment is so sensitive that we're actually able to see what's coming out here. And for some people, that's actually important because they may not consider that the package itself might be contributing to the amount of oxygen or water vapor that their product sees. So sometimes knowing that or gathering that curve and doing things like integrating the area under it to understand how many cc's of oxygen are going into their product that way could be very interesting, especially if you're packaging a serum or something like that. So getting back to what does the transmission rate look like, or the curves and things like that, I just talked about this outgassing curve and how it can come down and be very, very low and run for a long time. This is hours. This here, nearly 250 hours. It's 10 days running one test. These high transmitters can be really quick. They can be a matter of hours. As a side comment, in our laboratory, to guarantee that we're really at equilibrium, we set up a criteria that we want looking for a steady value over 24 hours. So even if a test is completed, or looks done in a matter of, let's say, 6 hours, we're still going to run a little longer just to extra assurance that it's not changing. This other graph here, I call a complex barrier. It's this gray curve here. What's interesting about that is actually it's a combination of the two. What we're seeing is on this one is an outgassing initially of the inside structure that's facing our carrier gas. But instead of, let's say, being a foil barrier, maybe it's this nylon or an EVOH or special coating that takes a little while for the molecules to wiggle through and diffuse through. And given time, they're going to come up and reach an equilibrium level. Like an EVOH might act like this, especially challenged with 100% oxygen versus room air. But this happens in real life with complex barriers. And that's one of the things I talked about. If you think about testing times, someone could like run the test and say, it's done here because it's not changing. So having a criteria of what is equilibrium, I think is important whenever you're doing testing, and being consistent with it. Because the ASTMs don't fully mandate what equilibrium is. They say it's an output that's not changing over time. And if you think it's not really done, come back later and check it. So in our laboratory, because we are an ISO 17025 accredited laboratory where we run permeation tests, we define that we're looking for a steady state over 24 hours. Now, in these two examples, they could actually take a really long time to test. So one thing I will point out is like in our laboratory, because I offer service, we do maximize, say, hey, we'll test at a maximum for 5 days. And that's when we call a test done. Unless you have a material that we know or we've characterized in the past, we know takes longer, then we can charge extra time for that. Because time on instrument is a cost. So that's important. If you have your own equipment, you may be doing R&D and you just need to, you'll take it out because you want this data. We've had some customers that have actually had us test for like 1,800 hours or, and longer to show maybe they've got a desiccant or a scavenger embedded in their package to make sure that in those cases that the transmission rates stay low for a long time. So the whole idea of time and permeation, it's a little different than any other physical tests. You do a peel test, it's pretty standard. Puncture test, pretty standard. You get to a permeation test, a little bit more things to consider. So I want to talk about the applications, or what are the things that we test. I think the neatest thing to talk about is packages. The schematics I showed you before talked about film structures mounted into a cell, but actually we do a lot of testing on bottles, on pouches, on trays, on capsules, on anything, syringes, polymer syringes versus a glass syringe, corks, and the like. If I zoom up a little bit here, here's an example of some packages that are open-sided, open-mouthed, and we can, this is actually, they're mounted to something that's going to allow us to purge nitrogen inside of them. Then we can surround the exterior of them with a controlled humidity or controlled oxygen environment for either oxygen or water vapor test. Here's someone looking at a cork, and they're looking at how good does the cork actually seal against oxygen ingress. And we have special things, special holders. This would be for like a K-cup, which is a very good barrier. But maybe you want to look at a lot of materials and get an aggregate, QC type thing. So we can group 5 of these together, actually double-sided 10 of these together to get a good idea of pass-fail, make sure that your production processes are working great. Trays, cartons, pouches. I think a good example of the testing, as I zoom up here on this, is here's a bottle. And what's nice about that is you can see that this is a bottle that someone wants us to analyze for oxygen transmission rate. Just not the bottle itself, but the bottle with the closure attached. And that can be a very important measurement because the bottle itself, typically bottles thermoformed, unaligned. Actually, they're not thermal. Well, some are, but they're these bottles, these packages of different types. They're usually very repeatable. They've got good material thickness, good distribution, good crystallinity. That all can be characterized on it. But the permeation test, if you look at the bottle by itself, they usually have very good tight tolerances between replicates, within 5% of each other, which is really nice. When you put a closure on it, though, that's a wild card. Whether that closure is a lidding to a tray, a lidding to a fruit cup, or a closure like this that's screwed on, you now can get ingress through permeating through the closure itself, but also maybe through the seals and the seams and the like. So for this type of sample, there's an ASTM F1307 that talks about drilling 2 holes in my package, putting my copper tubing inside of it, epoxying those in place, and then I'm sweeping this nitrogen gas inside of here. And then I've got oxygen on the outside that then's permeating through. And these lines will then carry it back into the instrument to the detector where we will quantify the OTR into the package. So we can do this with oxygen transmission rate and also with water vapor transmission rate, looking at how these gases move through the package walls. The last thing I'm going to talk about is the film testing. I kind of showed you the schematic for it. Again, I want to envision you what it kind of looks like. What we have here is our systems have a cartridge system. So we'll have a kind of like a bottom and a top to a cartridge. For the very standard cartridge, This area here defined by the O-ring is like 50 centimeters squared, roughly the footprint of like a coffee mug. And it'll take a sample that's roughly 4 by 4 inch squared, and we'll trim the corners. We'll mount it onto here. We've got an O-ring. And we've got this top area that we're going to seal with some sealing grease. This goes on top of it, kind of like a clamshell. And then your material to be tested is going to be in the middle here. And this allows us to sweep oxygen, water vapor, or CO2 underneath the film, and then our nitrogen or our carrier gas on top of the film. So that's really what's going on is these two come together, and then our instrument itself has drawers in it. It goes in, and then it's going to pneumatically clamp into place. Then it's a computer-driven system. And if you've got constant tests that you're always doing, you just kind of hit start. You put in some details about your material type, some ID. You'll control temperature, so you'll have to put in what temperature you want, what humidities you want, and the like. It's really nice. We have other cells sometimes for some more customized tests. These ones here are actually kind of neat. They're for like coated papers or paper boards, something called edge effect. It's an effect that basically, if I was just going to clamp my paper in this top cell here, because paper's so porous, you can actually get oxygen or humidity coming in from the edges, from the ambient around you that are impacting the transmission rate. So we've got ways to actually cut off or block those edges. Sometimes people can only provide samples that are small. They can't give us a larger piece that coffee mug size at like 4 by 4 inch square that we need. So we've got cells that can test smaller samples. So that works out very nice. In different instruments, some of our instruments actually can test 4 films at a time. It's still a cartridge system, but we kind of double stack the materials. So you'd have the sample. This would go on top of it. The next sample goes on there. Then this kind of comes on top of it. It all sandwiches together, almost like a really good, burger or anyways, like a turkey sandwich or the like. So we've got that. We have a lot of things. So this would be a cartridge for basically we call it a 4-cell system. So you can test 4 samples at a time. Then this cartridge here is kind of interesting for us is if someone has a little blister packet, think of or a gel cap, the packaging around that, could be for the saline, trying to understand what's going through the blister packet for a contact lens. That can fit in here. It seals in place, and now we're sweeping around that small blister, and then we're measuring how water vapor permeates out of it. So we have a lot of solutions. This poster doesn't have everything that we have, but it gives you a mindset that what we have is really good. I guess at this point, I've kind of completed kind of the overview. The things I want to touch on: what is permeation? There's real physics around it. Materials are lots of different ranges. We've got special instruments for very high and very low, and also for moderate barriers. Keep in mind that the measurement of this gas that's coming through is going to be dependent upon the temperature, what humidity is around it, the thickness of the sample, a lot of things in place. And things like the thickness of the sample or the material type is also going to impact how long does the test take. These are always just challenges that come up with permeation testing. So that's kind of the overview. If you have any questions, you can feel free to reach out to MOCON, AMETEK MOCON, and we'd definitely be able to help you out.